So rational functions is a Math 3 topic, so this should not be totally foreign to you, although we are definitely going to do some stuff with some limit notation that I know you did not do in Math 3. You may have talked about a few things, but I know you didn't do the full, limit notation sort of stuff that we'll be doing. So, a rational function is the quotient of two polynomials. What does that word quotient tell us that we're doing? Dividing, right? That tells you that you're dividing. So, all of these are going to look like fractions, right? Now, it is key for something to be a rational function, you do have to have a variable in the denominator. So, for example, like y equals 2x plus 3 over 5 is actually not a rational function. Okay, there's no variable in the denominator. This is actually just linear, and someone mark that one out. That one's linear. You could divide both the 2x and the 3 by 5, and you just get 2/5 x plus 3/5. It's just a line for that. So you must have a variable in the denominator. Okay, so we're going to be looking today at end behavior and zeros of rational functions for this. Okay, everybody good here? All right, so let's explore the end behavior of the most basic rational function that you can possibly have. Okay, the most basic rational function you can possibly have is 1 over x. Right? You have the most simple coefficient known to man, or I guess it's constant here. Constant known to man in the numerator, a 1, and you have just a single x in the denominator. Easy as it can be. So let's think about what happens as x approaches negative infinity, or x approaches positive infinity. I'm actually going to go positive first, just because it's a little easier to think about, although still, pretty easy to do either way. So, if I plug in 1 into this equation, I get 1 over 1, which of course just equals 1. And so what we're doing is the x value is approaching infinity. The x value is getting larger and larger and larger. So if I plug in 2, I get 1/2. If I plug in 5, I get 1/5. If I plug in 10, I get 1/10. If I plug in 100, I get 1/100th. And if I plug in 1,000, I get 1/1000th. Okay? What I like to do for this, sort of to illustrate what's happening here, right? If I am standing right here, and I want to walk halfway to my closet over there, right? So I'm going to walk half of the distance to my closet. So I go, eyeball it here. This gets me here, right? I've gone halfway to the closet. So if I go halfway to the closet again, 1, 2, 3, 6, so this will be right here, right? Going halfway to the closet again. I'm going to go halfway to the closet one more time. So if I go, there's 3 blocks. If I go 1 1/2, I'm right here. Went halfway to the closet. Okay. If I keep going halfway to the closet, theoretically, do I ever get to the closet? Theoretically, I'd never actually get there. Like if I was a particle, if I had no width, then I would never actually reach the closet. Now, obviously, I am not a particle, so I'm practically touching the closet over here already. But that's kind of what's happening here, right? I got 1, 1/2, 1/5, 1/10, 100, 1,000. What are our numbers getting closer and closer and closer and closer to? Like 1/1000. If I order pizza, if I was like, we're having a pizza party, and I order a pizza and I give you 1/1000th of the pizza, how much pizza have I given you? Basically nothing, right? So as that denominator of that fraction increases, the value just gets closer and closer and closer and closer to 0. Right? If we think about negative infinity as x approaches negative infinity, let's think about what would happen there. If I plug in -1, I've got -1, or 1 over -1, I guess. Either way, you just get -1 for that. Here, I would get 1 over -2. That would just give me -1/2. If I plug in -5, I have 1 over -5, which is just -1/5. You guys can see, same thing's happening here. I'll get -1/10, -1 over 100, -1 over 1,000. Now, my numbers are negative here, but what is -1 over 1,000 pretty close to? It's pretty close to 0, right? Just from the other direction, right? So that is also going to approach 0. So when we're talking about, when we're using limit notation, we're not talking about what we actually get right there. If you guys will shut your computers, we do not need those right now, so please put those away. If you'll put that away from me, please. Thank you. So we are going to just see this gets smaller and smaller and smaller and smaller, right? So that's what we're talking about here. When we're talking about limits, we may not actually reach that value, but we're getting so close we're practically there, right? And that's what we're looking at for the end behavior of these graphs. Now, for these graphs, a lot of times you get a number. For polynomials, when we did end behavior, what did we always get? Infinity or negative infinity, right? We never got a number whenever we were doing end behavior polynomial graphs. But for rational functions, you can get a number for those. So let's look at another scenario. Okay, now I am going to do the positives with, I'm going to actually do this out like by hand so we can kind of like see what's happening. So I've got x squared plus 2x over x to the third. Okay, so if I plug in 1, that is going to be 1 squared plus 2 times 1 over 1 to the third. So that's 1 plus 2 over 1, which is going to give me 3. So I'll get 3 for that. Okay, if I plug in 10, I've got 10 squared plus 2 times 10 over 10 to the third. Now, I'm making you do this out by hand for a reason. Like, I think it's helpful for you to see what matters the most here. We obviously are not going to have to do a lot of this by hand. So I've got 100 plus 20 over 1,000. So that's going to give me 120 over 1,000. Which we could just do it. Let's just do a decimal for that. There. That's going to be 0.120, 100 or 0.12 really. 120 over 1,000 would be 120 thousandths there. Okay. So the same thing for 100. Okay. Now it gets a little bit trickier here. I've got 100 squared plus 2 times 100 over 100 cubed. So when you're multiplying values with a lot of zeros together, specifically like that, they start with 1, right? So 100 squared is 100 times 100. You're just multiplying the ones together, which gives you ones, and how many zeros are you going to have? You'll have 4. 1, 2, 3, 4. You take the zeros basically from each number, right? So I've got 10,000. I'm really going to run out of room here. plus 200 over, and then I got to do 100 times 100 times 100. 1 times 1 times 1 is just 1. How many zeros am I going to have on that one? 6. 1, 2, 3, 4, 5, 6. So we get 1,000,000. So that is going to be 10,200 over 1,000,000. So that's going to be, like if you think of going with that 10200, and when you're dividing by 1,000,000, it moves the decimal place back 6 places. So 1, 2, 3, 4, 5. You got to go an extra spot, so you got to fill that in with a 0. So we're getting 0.0102 for that. I'm going to do 1,000 up here because I'm running out of room. I've got 1,000 squared plus 2 times 1,000 over 1,000 to the third power. So 1,000 squared, how many zeros is that going to have? 1,000 times 1,000. 6. 1, 2, 3, 4, 5, 6. Because first 1,000 has 3 zeros, the next 1,000 has 3 zeros, so it's going to be 6 altogether. We'll get 2,000 here. And then, how many zeros on my 1,000 cubed? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so this is giving us 1, 0, 0, 2, 0, 0, 0. Is that right? Yes, I think so. Over 1 with 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. Okay. That is going to be, like if I start with the 1, 0, 0, 2, 0, 0, 0, I got to move the decimal 9 places, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I get 0.001002 for that. What appears to happen here? We're putting zeros before and after the 1, which means what's going to happen to the value of this number if we keep putting those zeros before that 1? It's going to just decrease to 0 or awfully close to 0, right? So this also, our f of x as x approaches infinity is also 0. Now I had us do that by hand, not because you're probably going to be asked to do it by hand. Definitely, if our only objective was figuring out the numbers, this is what the calculator's made for, right? But I want you to see what matters the most here. Now, when the numbers were small, the 2 times 1 was our biggest number right here, right? Whenever we had a small number. But then, as the numbers got bigger, 2 times 10 was only 20. It actually now is like the smallest number in our problem, right? Whenever we think about these 3 numbers here. And then, over here, 2 times 100 is just 200 compared to 10,000 and 1,000,000, right? That number starts to become more and more and more insignificant as the numbers get larger and larger and larger and larger, right? Sort of the same thing here. Whenever I just plug in 1, 1 squared and 1 to the third are the same, right? But if I plug in 10, 10 squared is only 100, but 10 to the third is 1,000, okay? And then here, when I plug in 100, I've got 10,000 here, but I have 1,000,000 here. When I plug in 1,000, I have 1,000 squared is 1,000,000, but 1,000 to the third is 1 billion, right? So, what seems to have the biggest effect on how large those numbers are going to be as far as the equation goes? The exponent, right? The exponent matters the most when we're talking about large numbers. For small numbers, maybe not, right? But for large numbers, this 2x is totally insignificant. If it was a 5x, if it was a 10x, if it was a million x, it would eventually, for really large numbers, not matter anymore, right? That largest exponent is going to dominate what's happening whenever we're talking about end behavior. Because as the numbers get really, 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 really big, the only thing that really matters is whichever one has the largest exponent, right? So we could do the same thing with the negative. We are going to see something weird happen here, okay? I'm just going to do this one quickly. Here, you're going to have negative 1 squared plus 2 times negative 1 all over negative 1 to the third. When I square a negative number, what do I get? Positive, right? So I get a positive 1 minus 2 over, when I cube a negative number, I get still a negative number, right? So I'll have negative 1 right here. So negative 2 over negative 1 is going to give us a positive 2 for that. Now, for negative 10, I'm going to have negative 10 squared plus 2 times negative 10 all over negative 10 cubed. So that is going to give me positive 100 minus 20 over negative 1,000. Right? So that's going to be 80 over negative 1,000. So that's going to be negative 0.08 for that. You can put the extra 0 there if you want this to. Okay, so you can see, like, that denominator is negative every time, right, in this case. Now, I'm going to have, for 100, negative 100 squared plus 2 times negative 100 over negative 100 cubed. That is going to give me 10,000. Minus 200 over 1 million. So that is going to be, oh gosh, it's going to be like 9800, is that right? No, there's only one 9. Yeah, that's right, 9,800 over 1 million. Actually, not 1 million. What did I forget? A negative right there in that denominator. So that's going to be, like, I've got my 9800. I got to move that decimal 1, 2, 3, 4, 5, 6 places. I get negative 0.009800. So still here, like, I'm gonna skip 1,000. We won't go that far. It's still that denominator that matters the most, right? Now, I do have negative numbers, but what is the value of my function approaching? We're still getting smaller and smaller and smaller and smaller, right? So this still approaches 0 on the left-hand side as well. Okay, questions there? So whatever has the highest exponent is going to have the biggest effect on the function. All right, so let's think quickly about what happens if we've got a different scenario here, like this function. Okay, I would have, if I plug in 1, I've got 100 minus 1 squared over 1. That is going to be 99 over 1, which is 99. Now if I do 100 minus 10 squared over 10, that gives me 100 minus 100, which is 0, over 10. So I get 0 right there. If I plug in 100, I have 100 minus 100 squared over 100. Now this is going to give me 100 minus 10,000 over 100, which is going to be negative 9,900 over 100. Cross out those zeros. I get negative 99. Okay. Then I've got, I'll do my 1,000 up here. 1,000. Oh, sorry. It's 100 minus 1,000 squared over 1,000. I've got 100 minus 1,000,000 over 1,000. So I get negative 999. Hold on. 900, is that right? Yeah, I think so. Over 1,000. So that would cancel these out, move the decimal one place. I get like negative 999.9. Okay. Which term is mattering the most? Whenever we get to really big numbers, that 100, the x squared, or the x? That x squared. It's the biggest. It dominates the behavior of the graph, right? So we can see, now in this case, does it look like we're like getting closer and closer to a specific number? Probably just negative infinity looks like what's happening here. So negative infinity is what we're going with. Now, if x approaches negative infinity, let's think of how this might be a little bit different. It is going to be a little bit different. Here I'd have 100 minus negative 1 squared over negative 1. So I'm going to still get 99 on top, but what do I get in the denominator? Negative 1. So I get negative 99. And if I do negative 10, I get 100 minus negative 10 squared over negative 10. So I get 100 minus 100 over negative 10. I get 0 there. If I do negative 100 minus negative 100 squared over negative 100, you can see we get 100 minus 10,000 over negative 100. Okay, that gives me negative 9,900 over negative 100. Notice the numbers I'm getting are the same, but what's happening because of that denominator being negative? My sign's flipping here, and I'm going to get positive 99. What do you guys think I'll get for negative 1,000? Positive 999.9. Right there. What do I seem to approach here for as x approaches negative infinity? Positive infinity here. Okay. So again, we're not doing these all by hand because I'm going to make you do them by hand. I want you to understand what's happening with the numbers, and I think plugging those in by hand sort of help you see, right? Because there's going to be a very simple rule that I'm going to teach you, but I like for you to understand why, not just here's the rule. I'm seeing that a little bit. It's one of the reasons I don't love doing X method, and I'm thinking about maybe showing you the other way that I usually do for factoring, although I don't know if it matters that much, so I don't know if we're going to do it or not. But I might throw it in there. Like X method. I saw a lot of people, you were X method factoring, you were doing fine until there was a number in front of that X squared, right? Because even on the test, even after we went over a couple of them, some of you forgot that like last divide by 2 step. It's because you don't like equate it with what it means mathematically, like why it doesn't work if you forget that step. So I like for you to know like why these rules work. Okay. So the end behavior of a rational function is dominated by the term with the highest degree, or we could say largest exponent. If the term with the highest degree is in the denominator, as the x values decrease or increase without bound, the y values will approach 0. Okay? This is like the first 2 examples we had, right? 1 over x, we just saw the largest degree was in the bottom, we approach 0. And then we saw on the other one here, x squared plus 2x over 3x squared. Largest exponent is in the bottom. It didn't matter whether we approached from the left or positive infinity or negative infinity, our value still went to 0 for those. So if your largest exponent is in the denominator of your fraction, the bottom of that fraction gets the biggest, the fastest, right? And you end up with something really close to 0, right? Henry's doing fractions in 3rd grade right now, and he's like, he came in drawing like pizzas on my board, you know. He's like, everything. That bottom of your fraction is how many slices of pizza you have. If you have one pizza with 1,000,000 slices, you don't have much pizza, right? If you just look at one. So think about the bottom is your number of slices. Your number of slices of pizza significantly decreases how much pizza you're actually getting. So it gets close to 0 there. If the highest exponent is in the numerator, this is going to be slightly more complicated. As the x values decrease or increase without bound, the y values will approach either positive infinity or negative infinity. Okay? And then this is going to be a little more complicated because we have to decide whether we get positive infinity or negative infinity, right? So highest exponent in the numerator is going to follow the pattern. If I have ax to the n power over bx to the d power, okay, then f has the end behavior of the polynomial given by y equals a over b x to the n minus d. Okay, let's look at an example of that because that seems a little bit confusing. Okay, let's look at example 1 right here. Okay, in a polynomial function, or I'm sorry, rational function, the only parts that matter are the highest exponents, right? So first of all, we need to determine, is our highest exponent in the numerator or the denominator? You'll see for all 3 of these examples, highest exponent is in the numerator, which means we got to think a little bit harder. If the highest exponent is in the denominator, you just say 0 and move on. Those are the easier problems, right? So if we see that the highest exponent is in the numerator, our answers are going to be positive or negative infinity, for sure. We're not going to get a number. We're not going to get 0. We're going to get positive or negative infinity. But we need to look at the highest exponent in the numerator and the highest exponent in the denominator. And what we're going to do is we're going to think about what would happen if we had y equals x squared. Yes, that would be great. Yes, thank you. X squared over 3x. Now that would reduce, right? 1/3. You got 2 x's on top, only 1 on bottom, so that'd be 1/3 x to the first power. Okay, we don't care about the other pieces because when the numbers get really, really, really big, does it matter that you are adding 1 to this? I think of this like comedy sketch my husband will watch. It's like old Eddie Murphy comedy. And he's like talking about some woman marrying a billionaire. And she's like, he said, you know, if you marry a billionaire, you have to be a stay-at-home wife. What are you going to do? Go out and do hair for a living and come home and be like, I made $60 today. Put that with the rest, honey. That's $1,060,000 that we've got right now. This doesn't matter very much when we're talking about huge numbers, right? So we only care about these two. Our end behavior will be the same as 1/3 x to the first power, right? So we learned how to do that in the last unit, right? The right side is going to be whatever your coefficient is. 1/3 is positive here, so we get positive infinity for the right side. We have an odd exponent. So for odd exponent, that means we'll have opposite directions. We get negative infinity for this side. Okay, let's try another one. Example 2, numerator is the highest. We got to look at highest exponent in the numerator, highest exponent in the denominator. Nothing else matters when we're talking about x approaching very, very, very large numbers. So I've got y equals negative 3x to the 4th over x to the 3rd. If we reduce our x's, that just gives us negative 3x to the first power. So the end behavior of this graph will be the same as the end behavior of negative 3x to the first power. Okay. Which direction does the right side go for this one? Negative infinity. Because our 3 is negative here. Our coefficient is negative. And then what about the limit as x approaches negative infinity? What will we get for that one? Not also negative infinity. You want to go with the exponent once it's reduced. So not the 4 right here. What do you think, Asher? It's going to be positive infinity. Okay? Because we are looking here at once we reduce that exponent. Okay? So we reduce this and we just get x to the first power, which is an odd number. And when we have odd degree, our ends of our graph are going to go in opposite directions there. Okay, does that make sense? Okay. All right, last one. Again, we are looking only at highest degree in the top. That is not the first expression here. It's the second term, and it's also the second term here. Make sure you take the sign that's in front of that with it. So we're thinking about y equals negative 9x to the 4th over 3x squared. So negative 9 divided by 3 is going to give us negative 3. And then I've got x to the 4th over x squared. That's going to give me an x squared. Right? We just subtract those exponents. Think of having 1, 2, 3, 4 x's on top, 2 on bottom, 2 of them cross out. Right? Okay? So if we're thinking about the end behavior of this graph, Matthew, which way does my right side go? What's my limit as x approaches positive infinity? We'll get negative infinity, and we can tell that from the negative 3, right? And then, Shayla, what does the other side do for this one? Also negative infinity, because we have even degree this time, and both sides go down. And when I say even degree, you're thinking once it reduces, right? Not because this is a 4, but because this right here is a 2. Okay? All right, does that make sense? Okay, so it's similar to what we were already doing, but you got to sort of pull that out and reduce it. Okay? If the degree of the numerator is exactly 1 more than the degree of the denominator, the function will have, or has a slant asymptote. And we will learn more about that later, but we are not going to do that right now. Example 1 and example 2 would have what we call slant asymptote. So that's coming in the future, but we're not going to do it right now. Okay, questions here? All right, there is one scenario that we have not paid any attention to. And that is, what about if the degree of the numerator and the denominator are the same? Okay, now we're just going to use this for this one problem. I am going to pull the calculator out on this. You don't have to get your computers out. I'll just show it up here. I do want to make sure everybody knows how to, so we're going to type the function in, f of x equals 3 minus 6x to the second over 2x to the second minus 4x. If you want a table using Desmos, you are going to click on the gear right here, and then there's going to be an option right here that says create table. And it is going to come filled out with these numbers, but you can type in any numbers you want for the x values. So for example, if you are looking for -1, -10, -100, -1,000, you can type in -1, -10, -100, -1,000. Okay, and you can see what we're getting here is we're getting -0.5, -2.4875, -2.941. I mean, I'm not going to write the whole thing down. -2.994. What does it look like we're getting closer and closer and closer and closer to? Close. Not 3, but -3. There. Now, the table here does not guarantee that. You could go further. You could go like, oh, sorry. You could go like negative. Start just putting a lot of zeros, see what happens there. You know, definitely appears to be -3, right? We just keep getting closer and closer there. But this doesn't guarantee that that happens, but it's pretty close. Now, if I go through and do the same thing, but with positive numbers, you will notice that my first few numbers are a lot different, but I see something similar happen. I've got 1.5, I got -3.73125, I got -3.061, I got -3.006. What does it look like we're approaching this time? Still -3. We are approaching -3 from the numbers below -3 instead of above -3 this time, but we're still just getting closer and closer and closer to -3. Now, looking at that, do you see anything about that function that would tell you this might be -3? What did we say matters most? Highest exponents, right? So for this function, that is this and this, right? And if I got -6 over x squared divided by 2 over x squared, exponent x squareds cancel, right? And this just equals -3. That is not a coincidence. That's what's happening, right? For large numbers, the 3 and the 4x don't matter, and you get really close to just dividing -6 divided by 2. So, if the degree of the numerator is the same as the degree of the denominator, as the x values of the function increase without bound, or decrease, I don't know why I didn't put increase or decrease without bound there, the y values approach, I'm going to put a over b right here to match this function that I have put here. Whatever your coefficients are, you just divide those. So we don't need to go through a big, long, drawn-out like process for this where we make tables and plug in numbers, if I see, oh, my highest exponent here is 1, my highest exponent down here is 1, I could just take the highest 2 right here, and my limit as x approaches negative infinity of, now this was on your test, we really don't want to say y. The best thing to do is write the equation. I gave you a little grace on that on your test. Like if you said the limit as x approaches negative infinity of y, I didn't count off for that. That was okay. I'm going to go ahead and say, it's going to be the same in both directions, so I'm going to go ahead and say it equals the limit as x approaches positive infinity of 3x minus 5 over 8 minus x. And we're just going to get negative 3 for that one as well. I should have picked a different number so it wasn't the same answer twice in a row, but it's not always negative 3. But we're just doing 3 divided by that negative 1 right there. Now we can't quite do that on example 2. Why can we not do that as it is right now for example 2? The numerator is like in parentheses squared, right? For us to use this little shortcut, everything has to be expanded. Okay? Now, careful right here. T minus 3 squared does not equal t squared minus 9. That is incorrect. You cannot just square the t, square the 3. This means t minus 3 times t minus 3. And you have to distribute t squared minus 3t minus 3t plus 9, which is t squared minus 6t plus 9. So this is equal to t squared minus 6t plus 9 over 9 minus 2t squared. Okay, now we can just look t squared, negative 2, t squared. There's a 1 in front here. So my limit as x approaches negative infinity of h of t would be the same as the limit as x approaches positive infinity of h of t. And that is going to give me negative 1/2. Hey girls, did Anya give you guys a sheet to get signed for me? She has some, but I have a couple. It's okay. I'm going to go ahead and let you guys take one, but I need these back. Okay, yeah, all right. So if you can bring that to me.
Yeah, I'll bring it through you.
Yeah, well, it's got a parent signature on it, so you can bring it to me tomorrow sometime. At least, if you sign for your mom, at least don't let me know that you did. All right, let's see. I'm going to go ahead and take number 28 right there. Gianna. And bring me that paper back. It just tells you that those cost $100 if you don't bring them back to me, so don't lose it, okay? Bye. See it. Stats. Okay. All right. So, on the next slide, you see Bobo Botno eats CC. Did you guys use that some in Math 3? Bobo Botno. In Math 3, you're usually talking about horizontal asymptotes for it. It's also true for limits as x approach infinity or negative infinity, which actually we're going to see as we talk about this more. They're pretty much the same thing, right? Like if you want to know what the horizontal asymptote is, you need to do the limit as x approaches infinity or negative infinity. So Bobo Botno eats CC is just to help us remember the rules, right, for this. So is not an official, like, mathematical term. On the AP exam, you can't say this equals 0 because of blah, 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 no, HCC. You know, this is, I don't even know where this came from, honestly. My teacher taught this to me in high school. I remember doing it. And whenever I came here, people also knew about blah, 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 no, HCC. I don't know if they used this like in other parts. I don't know if there was like a training somewhere sometime that Surrey County went to that made them start using this. I don't know why we all tend to use this, but I'm pretty sure there's a lot of people that don't there somewhere. But bow is for bigger on bottom. That O right there is for 0. Bigger on top, not 1. This is specifically talking about horizontal asymptote, so there is not horizontal asymptote. That means that your limit is positive or negative infinity. If you think about a limit being infinity, a limit can't be infinity. If you go down the highway and you see a speed limit sign that says speed limit infinity, then is there a speed limit? There's not, right? In fact, I'd love a speed limit sign that said infinity on it. That would be cool to have. And then I could put a sign underneath it that says the limit does not exist. Because technically limits that equal infinity do not exist. But not 1 is because limits don't exist if they equal infinity or negative infinity. HCC is exponents are the same, divide coefficients. And that's just help us to remember the rules of what we do, right? So these questions should be fast. We don't have time to do it today, but we'll probably start with it tomorrow instead of a warm-up. Like, I'm going to have you guys do a few of these right now. But we will do like a quiz, real quick quizzes tomorrow to just kind of do a little more practice. The, like, homework I have for you tonight doesn't have this on it. It's going to have the next stuff. Because once you know the rules, I know we've spent a lot of time trying to understand why these rules work. But once you know the rules, these should be really fast. So do these for me. Tell me the limits for each one of these. right, check with your neighbors, see if you guys are getting the same answers. Alright, so, yes, but, you're thinking about, like, the highest on top and bottom, right? So, the exponents aren't the same here, so you got a square here, and like the first power. So, when you think of, like, dividing this, you would have an x with it, and then you want to think about what the end behavior of 1/3 x would do. So, like, if you had 1/3 x, if you have 1/3 x, the coefficient is positive, which tells you the right side goes up, and the exponent is odd, which tells you that you go opposite directions. So the left side of this goes up, down, the right side goes up, and then you just look to see this particular one is asking you about negative infinity, so you want the left side to get negative infinity for that one. Okay, here's what you should have for these. One is negative infinity. 2, these go down. 2 is -2. 3 is 0. 4 is positive infinity. 5 is negative infinity. And 6 is 3. Now, I think 3 should be the easiest one. Because if you have a bigger exponent on the bottom, you just get 0. You don't have to think much about it. It's just 0 no matter which way it goes. Okay? For 2 and 6, you have the same highest exponent on top and bottom. So you just divide those coefficients. So now, this one does have a little trick. This negative is out front. So that negative can be put in the top or the bottom. It does not matter which one. Don't put it in both places, because negative divided by negative is positive, and then negative cancels itself out. So you put it in top or bottom, but you just get -2 for that. For 6, you've got 3 over a 1 right here in front of that x squared. 3 divided by 1 will give you 3 for those. I think those are easier. For the others here, you've got here the limit as x approaches negative infinity. Of this, think about only your highest exponents. So you got x squared and 3x. You're going to divide them. When you divide them, this has a 1 in front of it. You get 1/3, and then you had 2 x's here, 1 in the bottom, so you just subtract those exponents. You get x to the first power. Then think about what the end behavior of that graph would look like, right? So the right side would go up because you have a positive coefficient. You have an odd exponent, so the left side goes down. Okay. Then once I get this little graph, I just look here to see whether I want the right side or the left side, right? X approaches negative infinity means left side. And you're going to do something similar here. You got 3x squared over 3x. 3 divided by 3 is 1. X squared divided by x is x to the first power right here. So that means I'm dealing with a right side up, left side down scenario. They're asking for left side, so I get negative infinity. For this last one, they again put a negative out here. So put that negative in the top or the bottom. I just moved it up here to the top since there's only one term there. So you got negative 1x to the third over 4x squared. Negative 1 over 4 is negative 1/4. If you subtract your exponents, you just get x to the first power. This time the right side goes down, left side goes up. They are asking for the left side, so you get positive infinity. Okay, questions? We're going to practice a little bit more with this tomorrow. We're going to see what we can do on this last little bit. It is pretty quick, but I don't know if we'll get to the inequalities. We may just have to be able to do the zeros probably. So, zeros of a rational function. Remind me again what a zero is, particularly a real zero. X-intercepts, right? If it's a real zero. I guess, I don't know if there can be imaginaries on these or not. I've never actually thought about that. We won't be asked to find them if there are. Rational functions have zeros at any value where the numerator equals 0, but the denominator does not equal 0. Okay, that is because 0 over a number, like 0 over 5, that equals 0. That is okay to have, right? That gives us a 0 of the function. But 5 over 0, that is undefined. Can't have 0 in the denominator of a fraction. And what we're specifically talking about here, which is an even crazier thing, is 0 divided by 0. We actually don't call that undefined. We call that indeterminate. Form. So what we're talking about here, we do have to check that the denominator does not equal 0 for these. So if we are asked to find all zeros of a function, what we want to do is factor the whole thing, if it's not already factored for us, right? These two are not factored. So we will factor the numerator. We will get x times x. For this one, we could multiply to get 3, add to get 4, so we need a plus 3 plus 1. In the denominator, how does that one factor? X plus 3, x minus 3. Okay? So, we are going to think about the zeros from the numerator. In the numerator, I would get x equals negative 3, and I would get x equals negative 1. Those come from my numerator, right? Those are my zeros, but what else did they tell me I had to check? The denominator cannot equal 0. So in that denominator down here, that is telling me here that x cannot equal negative 3 and x cannot equal positive 3. Does this conflict with my answers that I have for my zeros? It does, because right here I have x equals negative 3, but my denominator is saying, hold up, x cannot equal negative 3, right? So I got to cross this one out. That one doesn't count because it gives me a 0 in the denominator as well. You'll notice that happens when you've got factors that cancel, right? One on top and one on bottom. So the only 0 for this function is going to be at x equals negative 1. So the denominator doesn't matter much unless it cancels with the numerator, right? Let's do this last example and then we'll move on. We're not going to get to the inequalities, but that's okay. So we've got a factor. This is the more difficult factor in here. If we are X method in this, we got to do 3 times 4 to get positive 12. We need to add to get negative 7. What numbers work for that? Negative 3 times negative 4. But what do we have to do? Divide by the 3. And so I get negative 1. Here, the x goes in the bottom, so I get x minus 1 Ooh, gracious, I don't know what happened there. 3x minus 4. That's an x minus 1 right there on that first one. Okay, in the denominator, it's not x method factoring. What's the only thing I can do in the denominator? Factor out an x. So I'll just have x times 2x minus 5. Now you can also just kind of tell, do you have a factor that's going to cancel here, that's going to give you like the same value? You don't. So it is true that x cannot equal 0 and 2x minus 5 cannot equal 0, which means that x cannot equal 5 halves, but it's not going to come into play, right, because it's not going to overlap. So if I look at the numerator, I've got x equals 1. Is this 0? 3x minus 4, I got to set up myself a little equation. I don't know why it's doing that crazy thing. We're going to add the 4. 3x equals 4. We're going to divide by 3. So x equals 4/3. This time, my zeros do not conflict with my denominator at all. So I've got 2 answers for this one. So,